So far we've discussed optimal estimators of single random variables, but what happens when we have a vector, either a vector estimate or vector observations, or perhaps even both? Let's start with the observations. We'll assume that x is a scalar and that our observations are vector observations. So if we go back to our example of estimating the temperature tomorrow, maybe we don't just know what the temperature today was, but yesterday and the day before and the day before that. So now we have something that will give us some sort of a trend, and we could intuit that this is going to be a lot more valuable than simply a single observation. So that's this case. We have a vector observation. We have a scalar value that we're trying to estimate. So if that's the case, then x hat is equal to the expectation of x given y is still optimal. Nothing that we did in our derivation determined that we had to have a scalar observation, and so this follows straight out. We could go back through and make sure all the notation was correct, but we're not going to do that right now. In this case, x hat is just going to be the expectation of x given each of the individual observations, y0, y1, up to yn, for yn observations. Well, what if we have x also being a vector? In that case, x, we're going to say, has m plus 1 components here. And our estimate is going to have the same number, but we're just going to use m plus 1 scalar optimal estimators to get this. So let's follow this through and see what it looks like now that we have vector observations and vector random variables that we're estimating. So if we have that our error, I'm going to bold it because it's now a vector, is equal to x minus x hat, then we will have a separate estimator, call it hk of y, for each of the components of our vector x. And as mentioned before, that's simply this. And that minimizes the expected value of our error squared. Note that this is equivalent to another expression. We're not going to spend much more time with this, but it'll come up later, so it's good to see where it's coming from. So this is equivalent to the minimization of this expression, where we have over all hk from 0 to m, and we're minimizing e Hermitian times e. Well, that's going to be an inner product, of course, of the error vector and it'll give us the L2 norm of that error vector. An inner product is equal to the trace of the outer product, so this is equivalent to minimizing the same by tweaking our H knob, if you will. The trace of the expectation of EH, like that. So this first one is going to give us E0 squared plus, I guess since we used our Hermitian transpose, we're going to have like that. This expression right here is going to be a matrix. It's going to have E0 squared E0 times E1 conjugate, and so on and so forth. E0 conjugate, E1 squared, and of course the trace is going to grab these elements down the diagonal, giving us the same thing.